Hello. This time our topic is hard disk drive, one of the most popular storage device. Hard disk drive, this is the details, mechanical structure of hard disk drive. It has spindle and it has platter. And then it has a number of platter. And then on the platter, you write something. So in this disk, there are 3 platters. And then there is a media that reads and writes to the surface of the platter. This is called disk head. So this is disk head. And disk head is attached to the arm, which is called the disk arm. So in here, there are 3 platters. And the platter has 2 surfaces, the upper side and downside, and this platter has 2 arms and 2 heads, and each of the head with each surface of the disk platter. So from the other view, this is platter, this is spindle, and there is a arm that rotates and raises the surface of the platter. So this arm goes right here to here. So in some disk drive, it has 2 platter, and in some disk drive, there are 3 platters. And in some hard disk drive, it has 2 platter, but it only uses 4 out of 4 surfaces available. Some platters use 2 platters, but some disk uses only 3 surfaces. That's how it works. Okay, so this is basic geometry. There is an arm, and there is disk head. And then if you fix the spindle and if you rotate the platter, then if you fix the disk head, then it will form a circle. This is a circle. This circle is called a track. And remember, there is very, very important unit that is called a sector. This is minimum unit of the write or read from the disk. This is sector. So in this case, there's sector 0, sector 1, sector 2, sector 3, and sector 11. There are 12 sectors in a track. This is the geometry of the disk. Okay, so there are multiple sectors. Assume that the platter rotates in counterclockwise direction. So from outer platter, it goes into inner platter. And so if you want to read a sector, then you have to first move the arm to place the arm to the right track, and then you have to rotate the platter to place your desired sector underneath your head. So this is the basic mechanism of how you read the disk. So there is rotation and there is seek. Rotation is an act of rotating the disk platter. And time to rotate the disk platter is called rotational delay. For the hard disk drive, if the full rotation takes about 8 seconds, then the average delay becomes half of the entire time to rotate the platter. Right here. For example, if you want to, the current head is on the sector 30, and if you want to read sector 24, right, then you have to rotate the entire platter in 180 degree. That is the half of the entire rotation. The rotational delay will be half of the rotational delay R. For rotational delay R. Okay. And the second important thing, actually the most important thing, is seek time. Seek time is the time to place a disk head to another track. So it's time to move head from one track to another. This is called seek. So this is the most time-consuming behavior in hard disk drive. This is called track. But this is mechanical. Remember, this is mechanical arm. This is mechanical arm. So when you move the mechanical arm, if you let's draw a graph. This is distance, and you have to move the disk head from track T1 to track T2, and then this is velocity, where the arm is moving. Then at the beginning, the disk arm was fixed at a certain track, and then it keeps increasing its speed, and then coast, and after it reaches near the region of the destination, the target track, and then the head speed goes down. So the platter rotates at the same RPM, rotation per minute. However, when the disk head moves, it takes first acceleration, and coast, and deceleration. This is called. And when it reaches near neighborhood of the destination track, then it has to settle it has to precisely place the disk head to the right track, and it is called setting. So this the seek phase consists of acceleration, coast, deceleration, and setting. So from here to here, we can think of it as acceleration, accel. And from here to here, we think of it as a coast. And from here to here, we call it a deceleration. Okay. And then after it reaches the neighborhood of target track, it has to perform some fine-tune to precisely place the disk head on top of the desired destination track. So that we call a setting. So this is total time for seek. Okay. Now let me explain the concept of track skew. Track skew is an angle between adjacent tracks where the starting sector of each track is differ. For example, here the track 0 in an outermost track, the sector 0, which is the starting track of the outermost track, starts here. And then in the inner track, the starting track 12, starting sector number 12 starts here. And then in the third most inner track, the sector starts at 24. So there is an offset of angle from the adjacent tracks with track degree delta. This is theta, for example. And then from the second track to the third track, there is another angle offset, theta. The reason we introduced this one is to optimize the sequential read operation. If you consider a situation where we read from 0 to sector 31, for example. So we are going to read all the sectors, 1, 2, 3, 4, blah, da, da, and 31. Excuse me. And then what we do is first read the entire track like this. And then you have to switch the track from here to here. But when we switch the track, the platter rotates because the platter rotates at a constant revolution. So during that period, for example, it's 0.1 milliseconds, let's say. Time to switch a track is 0.1 milliseconds. During that time period, the platter has been rotating. So to place, if we do not introduce track skew, then we have to lose one rotation to find a starting track starting sector of the next track. So we introduce a track skew, this amount, that when you switch the track, the desired sector is just underneath your head. That's track skew. Now we explain the concept of multi-zoning. Multi-zoning. There are two types of bit density. One is angular bit density. Angular bit density. And another one is linear bit density. Linear bit density. So, in old days of hard disk drive, angular bit density is constant. So no matter what the tracks are, we place the same number of sectors in the track. For example, here, like a pie chart. So here in this plateau, okay, independent of perimeter, every track has precisely the same number of sectors. So each track has same number of sectors, which is 8. So in this disk, the angular bit density is constant. However, of course, the outer track has much larger perimeter than the inner track. So in most of the recent hard disk drive, they make that outer track tends to have more sectors than inner track to make the linear bit density almost constant. So in this example, outer track has 12 sectors. However, inner track has 8 sectors. So, in multi-zoning, hard disk controller partitions a set of tracks into a number of zones. For example, this is innermost zone, which consists of like hundreds of tracks. And then this is another zone, which consists of like another thousands of tracks. And this is outermost zone, and it consists of another thousands of tracks. So within each zone, the number of sectors per track is the same. So this is zone 1, this is zone 2, and this is zone 3, for example. So this technique is multi-zoning. Multi-zoning. What is this for? Of course, to increase the disk capacity. Of course. Okay, so then next concept is called track buffer. It is also called a cache. So hard disk drive has small amount of DRAM. It is used to hold data read from or written to the disk. So it allows the drive to quickly respond to the request. So for example, there is 30, 22, 10, 4, and 27. And then instead of writing each of these blocks sectors directly to the disk surface, it first buffers those requests to the buffer and then place it to the track. Also, on the other hand, when you read some of the sectors from the track before, for example, let's say you are reading 32 and 35, and for example 27, and then current head is at 30. Okay, and then the usage of track buffer is as soon as it reaches the target track, it directly starts to read the whatever sectors they are underneath the head and reads them all, and then place it to the track buffer instead of spending time on fine-tuning, finding the right sectors he wants to read. So that's the usage of the track buffer. So this is allow the drive to quickly respond to the request. So there are two types of approach in utilizing track buffer. One is track write back, and then the other is write through. In write back, acknowledge the write has completed when it has put all the data in its memory. So in write back approach, which is a solid green line, when the host sends a write request, for example, and then right after it, the associated data blocks that needs to be written to the disk surface have been transferred to the track buffer, the disk controller acknowledges that write has completed. Like this. So write the data blocks to the track buffer, and then once the data block reaches its track buffer, it acknowledges the completion of the I/O. That is write back strategy. The other one is write through strategy. And in write through strategy, it writes to the track buffer and it directly writes to the surface of the platter. And then once all of them is written, and then it sends back the acknowledge to the host. So it takes a lot longer, and so this is very rarely used. So there are two approaches, and write back and write through. Okay, so let's do some math. In writing or reading to the disk and from the disk, what you have to do is you first have to move the disk head to the right track, and then you have to rotate the platter to find the right sector, and then you do transfer. So it consists of three phases: seek, rotate, and transfer. So time to do an I/O consists of three phases or three components: T-seek, and T-rotate, and T-transfer. So I/O performance or I/O rate is computed as the amount of data you want to transfer divided by the time to transfer those data. That is R/I/O. Let's compute the actual performance of hard disk drive. We're gonna compute the performance of two hard disk drive. First one is Cheetah 1500, not 15,000. This is for server. They use SCSI, and this is very fast. It's a 15,000 RPM drive. This is Seagate Barracuda. This is for PC. This is only 70 to 100 RPM drive, but and in terms of capacity, it's just much larger. So this is 1 terabyte. Capacity for Cheetah is 300 gigabytes. Okay, so so the capacity of Cheetah is 300 gigabytes. It rotates at 15,000 RPM, and then average seek time is 4 milliseconds. And max transfer rate is 125 megabytes per second. It has 4 platter, and it has 16 megabytes of cache, and the interface is SCSI. In case of Barracuda, the capacity is 1 terabyte. It rotates at 7200 RPM, rotations per minute. This is RPM. This is rotation per minute. And then average seek time is 9 milliseconds. So apparently, the PC disk drive Barracuda is much slower than the server disk drive Cheetah. And the max transfer rate is 105 megabytes per second. It has 4 platters. And then cache, it has two types of disk, each of which has different cache size: 16 megabytes or 32 megabytes. The interface is SATA. So the seek time is 4 milliseconds. Average seek time is 4 milliseconds. And oh, sorry, I'm going to explain the cheetah hard disk drive performance. The rotation time, average rotation time, is time to revolve a single time to take a single revolution divided by 2, because we are talking about average. So for 15,000 RPM drive, it corresponds to 250 rotations per second. It corresponds to 4 milliseconds per 1 rotation. So if you divide it by 2, then single rotation, average T rotation corresponds to 2 milliseconds. The T transfer is 4 kilobyte divided by 125 megabytes per second. So if you transfer 4 kilobyte at the speed of 125 megabytes per second, then time to transfer a single 4 kilobyte block corresponds to 30 microseconds. So if you sum them up, rotation time, seek time, and transfer time, then total time for sending 4 kilobyte drive corresponds to 6 milliseconds. So this is just time for transferring 4 kilobyte block. And the speed, the rate of I/O, it's 4 kilobyte divided by time to transfer it for 6 milliseconds. Okay, it's 0.6 megabytes per second. It's very slow, very, very, very slow. Not only slow, it's extremely inefficient. Why is that? Think about this time. So you are spending 6.03 millisecond to transfer 4 kilobyte. However, out of that, only 0.03 milliseconds is an actual time to transfer a disk block. Rest of the time for transferring a disk block is spent on moving the disk head and moving the disk platter. So this is very inefficient. This guy is emotionally down because it's inefficient. Okay, let's move into the next PC disk drive, the Barracuda. Here, the seek time is 9 milliseconds, and then rotational speed is 7200 RPM, so it takes 120 rotations per second. It corresponds to 8 milliseconds per rotation. So if you divide it by 2, then average rotational delay is 4 milliseconds. And then transfer time is 38 microseconds. So TIO, time to send a block, corresponds to 4 milliseconds plus, 9 milliseconds, which is seek time, plus 4 milliseconds, which is rotational delay, and then 38 microseconds, which corresponds to the transfer time. So, for transferring 4 kilobyte data block, the speed corresponds to 0.31 megabytes per second, which is about half of the cheetah drive. So this is the reason why the server vendors or server system purchase the lot more expensive but a little bit fast disk drive. Time to perform random I/O. Let's compute the time to write sequencer blocks, lots of blocks in sequencer manner. Let's say we are transferring like 100 megabytes in large fashion. Then for Seagate, for cheetah drive, 15,000, the seek time is 4 milliseconds. Rotational delay is 15,000 RPM. So as same as before, average rotational delay is 2 milliseconds. The seek time is 4 milliseconds. And then the transfer time for transferring 100 megabytes is 800 milliseconds. In that case, time to transfer 100 megabytes data chunk corresponds to 100 milliseconds. So here, It's happy because most of the time for transferring 100 megabytes data blocks is consumed by data transfer time. Okay. So in that case, the I/O rate, the I/O performance corresponds to 125 megabytes per second. Here, the vendor specified max transfer rate corresponds to 125 megabytes per second. And when you transfer consecutive 100 megabytes, it reaches its 100% utilization. So this is why most of the file systems and most of the application tries to make the I/O size as large as possible and tries to avoid random write. Here, the disk utilization is nearly 100% because out of 860 milliseconds, 800 milliseconds has been spent on sending the data block, and only the 6 milliseconds out of 806 millisecond has been spent on moving the disk drive head and disk platter. So we are very happy now. Very, very happy. Because we have fully exploited the performance of the underlying hard disk drive. It is the same for the PC drive Barracuda. So seek time is 9 milliseconds. The same. The rotation delay is also 4 milliseconds. It's the same as before. Transferring 100 megabytes takes 150 milliseconds. So time to perform an I/O corresponds to 163 milliseconds. So sending 100 megabytes with 150 milliseconds corresponds to 105 megabytes per second, which is the same as vendor specified maximum transfer rate. So if we write 100 megabytes in consecutive fashion, then the application should be able to fully exploit the performance of underlying hard disk drive. That is very desirable. So we are happy now. Because we have successfully utilized the performance potential of the underlying hard disk drive. So let's summarize it. For Cheetah and for Barracuda, random I/O performance is nearly doubled in Cheetah. For 4 kilobyte random I/O, Cheetah yields 0.66 megabytes per second, and Barracuda it has yielded 0.3 megabytes per second. Random I/O is not good, but for sequential I/O, both of them, when you write 100 megabytes data chunk, they were able to fully utilize the underlying performance. So this is why we have to carefully design the software for an I/O to use sequential write rather than random write. Okay, so now think about the term, the disk scheduling. Disk scheduling is an algorithm to move a disk head based upon the request from the host. So first one is shortest seek time first. There are a queue of I/O requests from the host, and then this controller has to order a queue of I/O requests by track, and we have to picking the request in the nearest track to complete first. So this is shortest seek time first. Here, there are the current disk head is currently on top over the sector 30, and then there are 2 requests. One is for sector number 2, and the other is sector number 21. Okay. In this case, even though there are 2 requests in the queue, and even though 2 has arrived earlier than the request for sector 21, on the scheduling algorithm, shortest seek time first algorithm, they used to issue request 21 first and then used sector 2 number 2. So that is shortest seek time first. But shortest seek time first has an issue. First, the drive geometry is not available to the host operating system. So usually they perform the shortest seek time first using the nearest block first algorithm because they know the linear block number or linear block address. Linear block address. But the problem is that even they do shortest seek time first, or they perform nearest block first algorithm, both of them makes a certain request under the starvation. Because let's see, there is a disk plateau, and disk head is under the rightmost position, rightmost track. This is disk head. Okay, and then there is like a request for sector 20, and there is another request here for sector, for example, let's 1000. So in the queue, there is a request for sector 20, and there is a sector 1000. But somehow, in the middle of reading this sector 20, there is a bunch of requests for like 20, 20, and 21, 198, stuff like that. And all the subsequent request is adjacent under the current disk position. And in that case, the request for the sector that is farther away from the current disk position will not have sufficient chance or will not have fair chance of getting serviced. So in that case, a certain request is under starvation. Let me explain the disk scheduling algorithm. Disk scheduling algorithm is how to order the services for the requests in the queue. The first one is first come, first served. First come, first served. So this is the queue of requests, and this is the order in which they arrive. Then first come, first served is each request is serviced at the order which is arrived. So this explains how it is serviced. 98, 183, 37, 122, and 14, 124, 65, and 67. This is the precisely order in which all the requests has arrived. The total number of distance, which represents the disk scheduling efficiency, is 604 cylinders or tracks. Next algorithm is shortest seek time first. So it selects the request with the minimum seek time from the current head position. So this is shortest seek time first. The head is currently at 53, okay, and then 53 go to 65, and then go next to the 67. So when it seeks the next request to service, it searches the nearest request and services them. There is one issue in shortest seek time first. It causes starvation because if some dominant fraction of requests are clustered on some region, then farther away requests will not have fair chance of getting serviced. So another family of algorithm is called scan. So disk arm starts one end of the disk and moves towards the other end, servicing the request until it gets to the other end of the disk, where the head movement is reversed and servicing the request. So sometimes it's called elevator algorithm. Next head movement, it reaches 208 cylinders. So let's consider the scan. Let's assume that current head starts at 53. So it goes one direction towards the end, and then goes to the other end in one direction. So this is called a scan and also called as elevator. Okay. The problem of the scan algorithm is that the request on the innermost cylinders and the request in the outermost must have cylinders will not have a same chance as the cylinders in the middle part, request in the middle part of the cylinders, because in innermost tracks and outermost tracks it has only one chance of getting serviced, but the requests in the middle part of the tracks, they are serviced on this direction as well as on this direction as well, so it has a double chance of getting serviced. So to resolve the situation, they have come up with an idea of C-scan. It is called circular scan. Provides more uniform wait time than scan, because in circular scan they services the request in only one direction, so at each track has the same chance of getting serviced. So head moves from one end of the disk to another and service request as it goes, and when it reaches the other end it immediately returns to the beginning of the disk without servicing any request on the return trip. So that is what C-scan is for. It treats the cylinders as a circular list. Like circular list means like this. Wraps around from one last request to the first one. Okay. So assume that head is currently at 53, and let's start the circular scan. It goes only one direction. Okay, until it reaches the end and then comes back at the other end of the disk and then services it. This is circular scan. Here, there is some point of improvement. First, after servicing 183, actually it doesn't have to go to the outermost end of the track. Another issue is that there is a request at track 14. However, this head goes all the way back to the beginning of the cylinder, which is not necessary. So to solve the problem, they come up with the variance of C-scan, which we call C-look. In C-look, arm only goes as far as the latest request in each direction, and then reverses direction immediately without first going all the way to the end of the disk. So that's C-look. Okay, so let's start. The head is the same as before at sector 53. Oops, sorry. It goes in one direction to the outer direction or inner direction, and then it goes to sector 183, and then without going to 199 it immediately returns to the beginning of the cylinder, but instead of reaching the very first track, it goes as inner as the starting sector resides, which is sector 14. Okay. So this is the end of C-look algorithm. So there is a number of issues for selecting the disk schedule algorithm for hard disk drive. Shortest seek time first is the common, and it has a natural appeal. However, scan and C-scan perform better for heavy load. So the performance of the hard disk drive while scheduling depends on the number of types of the request, and of course the request for disk service can be influenced by the file allocation method. So both shortest seek time first and look algorithm is a reasonable choice for default algorithm. And there is another issue such as IO merging. And so And IO merging the continuous request into a single 2-block request. So by waiting, a new and better request may be arrived at disk. So there is 33 and there is 8, and then it waits for another request, and then it comes 34, and then we can issue 33 and 34 as a single disk request, and then performs 8. That is called IO merging.